In this video, we're adding GPS waypoint navigation to our autonomous robot, allowing it to drive to real-world coordinates while continuously correcting its heading and avoiding obstacles. We are following the robot and monitoring everything through a live web dashboard featuring a real-time map working over a mobile data connection. In the last video, we built an autonomous robot capable of avoiding obstacles all on its own. Using laser and ultrasonic sensors, it could scan the environment, choose the clearest path, and keep driving without any human control. Today we are going to use a GPS module with a built-in digital compass and some custom navigation code. We'll teach this robot how to understand where it is, where it needs to go, and how to make smart decisions along the way. Can this GPS module actually navigate a robot or RC car accurately enough to be useful? And can this tiny robot navigate through a large park all on its own? What features can we program along the way to give it the best chance? Let's take a quick look at how the navigation system actually works. The GPS module continuously reports the robot's current latitude and longitude. Whenever a mission starts, the ESP32 compares that position with the next waypoint and calculates two important values. The first is the distance to the waypoint. The second is the compass bearing, or the direction the robot needs to travel. The robot then rotates until it's facing that heading before driving forward. While driving, the digital compass constantly checks the robot's direction. If it begins drifting left or right due to uneven terrain, the ESP32 automatically adjusts the motor speeds to steer it back on course. Instead of simply driving towards the waypoint once, it's continuously checking its position, recalculating the bearing, and making small steering corrections as it moves. To eliminate the jittery weaving motion while driving, let's add a low-pass exponential moving average filter to the compass readings. The problem with electrical noise and uneven terrain, it causes the data to fluctuate rapidly, which can cause our steering controller to go into a constant overcorrection loop, fighting itself the whole time. By running the compass through this filter first, we can get those spikes smoothed out before they ever even reach the drive logic. The robot stops reacting to noise it should be ignoring. Combined with a tighter deadband and a lower proportional gain, it can now hold a rock-solid heading towards its target waypoint without the weaving. Of course, the real world isn't an empty parking lot. If the obstacle sensor detects something in front of the robot, it immediately stops, scans the surrounding area, chooses a safer route, then drives around the obstacle, recalculating the GPS bearing before continuing towards the same waypoint. It repeats this process over and over until it reaches the destination. Once it arrives within 4 meters of the waypoint, it automatically moves on to the next one. A magnetic compass points to magnetic north, but GPS calculations use true geographic north. Depending on where you live, the difference or magnetic declination can be anywhere from 5 to over 20 degrees. If you don't correct for this, your robot will most likely drive off at an angle. You can use this website here and click on your exact location to get the magnetic declination for your area. We've also included a calibration in the startup routine. On boot up, the OLED fires up a live graphical compass dial showing real-time heading and cardinal directions. We point the robot towards true north, and as the timer hits 0, the ESP32 locks in our baseline reference and magnetic declination. Immediately after alignment, the robot performs a 360-degree turn. While spinning, the ESP32 samples hundreds of magnetic data points across the X and Y axis. This measures the hard iron distortion caused by the onboard motors, battery, or metal frame, shifting our raw compass data into a perfectly centered circle. Let's head outside to a large park and see how accurate this actually is. The robot connects to your phone's Wi-Fi hotspot, placing it on the same network as your phone. It will then display its given IP address on the OLED screen. Type this address into your phone's browser to access the web server. The robot itself doesn't need any internet connection. It works off GPS satellites and streams data and receives commands locally. However, the live map feature does require an active internet connection on your phone to load the background map data. To track the robot and handle mapping, we're using Leaflet.js, a lightweight open-source JavaScript mapping library. The best part is it's 100% free and requires 0 API keys or accounts to run. Instead of setting up an external web server, we embed the entire mapping UI inside a single lightweight HTML file stored directly on the ESP32's flash memory. When you connect the robot to a local Wi-Fi network, the ESP32 serves the dashboard right to your phone or laptop, pulling map tiles dynamically from OpenStreetMap while rendering live breadcrumb trails and waypoints via WebSockets. By default, Leaflet gives you a standard blue location pin, but instead of using a static pin marker on the map, we want to see exactly which direction the chassis is pointing in real time. To do that, we replace the custom pin graphic with our own custom HTML containing a vector arrow. Instead of loading an image file, we created in JavaScript containing an inline SVG arrow. This keeps it razor sharp on high-density phone screens without taking up memory on the ESP32. Because it's rendered as an HTML element, we can dynamically apply CSS rotation to it in real time. Once our custom arrow is sitting on the map, the ESP32 takes over. Every half second, it sends a fresh data packet over a WebSocket connection right to the phone's browser. JavaScript grabs those new latitude and longitude values to slide the arrow to its new position, and then applies a single line to spin the arrow to match our compass. The result is a super smooth telemetry feed that updates in real time, completely locally with zero lag. We can see the robot making its way through the park, with its home position being set automatically once a GPS fix is acquired. It takes about 30 seconds to 1 minute for the module to connect to satellites. The more satellites it receives, the more accurate the GPS signal is. I found it to be more than accurate enough for backyard tinkering, but you may get different results depending on your location and the modules used. For this update, we've upgraded our web ground station with interactive safety layers and real-time environmental awareness. We integrated Leaflet map tiles so you can instantly switch between high-resolution satellite imagery, topographic maps, and standard street views. We've included a live rain viewer weather radar overlay to track incoming rain as you plan your path. Beyond map visuals, we added dynamic hazard protection using live geospatial APIs. Before sending a navigation command to the vehicle, the dashboard checks OpenStreetMap's Overpass API and the Open Elevation API to check for nearby bodies of water or excessively steep terrain. If a waypoint lands in a high-risk zone, like a pond or a steep cliff, the system flags the hazard in red and blocks the movement command, keeping the robot safe before it even moves. And to make sure the rover doesn't just blindly drive in a straight line through trees or over cliffs, let's include OSRM trail pathfinding. When you toggle pathfinding on and tap anywhere on the map to set a waypoint, the dashboard connects to OpenStreetMap's foot routing engine. It instantly calculates a safe, walkable route along known park paths and foot trails. It also draws a purple navigation line right on the leaflet map and then streams every single waypoint down to the ESP32. This means instead of crashing through the brush, the rover intelligently stays on a safe known path all the way to its destination. This project is just a first step towards building a fully autonomous outdoor robot. We've gone from simple obstacle avoidance to real GPS waypoint navigation with live mapping, continuous heading corrections, and automatic return to home capabilities. If you'd like to check out the code, as always it's linked below in the description. If you enjoyed this build, hit the like button, make sure you subscribe so you don't miss the next one.